In this video, we are going to discuss arc length of a path. This first slide shows all the main points that we will be discussing. There's one more example, and by way of review, there are two problems for you to try. We will start by finding the length of sigma. So once we have a path, we can find its length by integrating the magnitude of its velocity. In other words, the magnitude of its first derivative, and integrating from a to b dt. And in 3 dimensions, this is the formula that we will have. And intuitively, what this is the speed times the amount of time traveled from start time A to end time B. An example of this formula is to calculate the arc length of the curve sigma of t of r cosine t, r sine of t, for t going from 0 to 2 pi. And you might recognize this from our last video as the parameterization of a circle of radius r. And in case you don't remember, here is your x-coordinate, r cosine t. Your y-coordinate is r sine t. So if you take x squared plus y squared, you're going to get r squared cosine squared t plus r squared sine squared t. And the cosine sine combined to give you 1, and you're left with r squared. So what you have is x squared plus y squared is equal to r squared, which is a circle of radius r. So this is an example you'll see many times, so it's worth getting to know. Here, getting ready to plug into my formula, I need the derivative of my sigma. So I take my derivative, that gives me my velocity, if you recall. So the derivative of this with respect to t is minus r sine t. The derivative of r sine t with respect to t is r cosine t. I plug it in. I need the magnitude now of my velocity. So that's the square root of r sine theta, negative r sine theta squared, plus r cosine t squared. You can see that these two combine, and I get the square root of r squared dt, and that will integrate to become 2 pi r, which is exactly what we would expect since this is the circumference of a circle of radius r. Also note, if we had allowed t to go from 0 to 2 pi, 4 pi, if we had integrated from 0 to 4 pi here, we would have gotten 4 pi r, which is also what we would have expected because we will have gone around the circle twice. We will have traversed the path twice. It is often convenient to have a formula that you can just plug in a point, and then you get the distance from a starting point. So that's called the arc length function. So we define this formula s of t, or this function s of t, and it really is the same thing as sigma t. So again, we have sigma prime of t is just the same thing as ds dt, which is dx dt, derivative taken with respect to x in the I direction, derivative of y with respect to t in the j direction, derivative of z with respect to t in the k direction. And so the magnitude or the speed is just ds dt, magnitude, and we have the same formula here. But then what we do is we use this function to calculate how long a path is from P naught, a starting point, or A. So we derive this S of t is the integral from A to whatever point t you want to plug in. So it's going to tell you again the distance from a starting point A that's given to the starting point, to the ending point t that you plug in, and you take the magnitude of sigma, integrate with respect to tau, and this tau is just our variable of integration. So for example, if we have our path and it's a helix, a cosine t, a sine t, bt, and we have a starting point at x naught at t equals 0, in which case our starting point is a, once we plug it into here, is a 0, 0. We want to find a formula s of t. So in other words, what this formula is going to tell us is how far we are from a 0, 0, how far this point t is from a 0, 0, and we just want to plug in the point t. So we can go through all of this definition here, but sometimes we just want to have this formula figured out. But honestly, after this chapter, you're not going to see this formula again, at least not in this class. You'll just be going through this calculation here. I made some notes over here. So x prime of t is going to be minus a sine of t, a cosine t, and then b. And then if I take the magnitude of the derivative, it's square root of a squared sine squared t, a squared cosine squared t plus b squared. And so the sine squared cosine squared become 1. So what I'm left with for our integral is square root of a squared plus b squared. And if I want to know the distance from the point t equals 0 up to t, then I'm going to use those as my limit of integration. Since a and b are just constants, then this is just my final integral is my final answer is going to be square root of a squared plus b squared times t. Another note or another example is that the definition of arc length can be extended to include paths that are not of class C1, but that are formed by piecing together a number of C1 paths. So for example, if we want to find the arc length of the path sigma from -1 to 1, such that t gets mapped to the absolute value of t, the absolute value of t minus 1/2, and 0, we can look at this and we can see the path is not differentiable at t equals 0 or t equals 1/2 because there's a sharp curve in the absolute value function. So we can take the interval c1 goes from -1 to 0, c2 can go from 0 to 1/2, and then c3 can go from 1/2 to 1. And then we've covered our entire interval -1 to 1, but we stop at each of the points where it's not differentiable. In this way, our path sigma is piecewise C1. So between -1 and 0, the absolute value of t is going to be negative t, right, because I'm in the negative numbers. And then absolute value of t minus 1/2 is negative t plus 1/2, and then 0, 0. I can calculate my derivative here, and then I can do my integral between -1 and 0 and get square root of 2. In my interval C2 between 0 and 1/2, now my square root of t is just equal to t. My t minus 1/2, though, is going to be still minus t plus 1/2 because it's the absolute value. And then we have 0. I can take my derivative, and then I can take my integral from 0 to 1/2. And last, for C3, my absolute value of t, when we're looking at 1/2 to 1, is t. The absolute value of t minus 1/2 is t minus 1/2, and then I get 0. I take the derivative, I take the integral, and then for my final answer, I can add up c1, c2, c3, and I get 2 square root of 2. Two more quick definitions. The unit tangent vector, capital T, of the path, sigma, is the normalization of the velocity vector. In other words, the unit tangent vector, t, is just the velocity vector divided by its magnitude, so it has unit length. The curvature of the path is the angular rate of change in the direction of t per unit change in distance along the path. So curvature, designated with this k of t, is equal to the derivative of t with respect to s and the derivative of s with respect to t. So the thing about curvature, so it kind of captures how much curve there is. So a small k, so t is changing a little bit as the curve progresses. Here, as the curve progresses, t is changing much more, so it's a larger k. Here we have one more example. So a particle moves along the hypercycloid, x equals cosine cubed of t, y equals sine cubed of t, and t goes between a and b. What are the velocity and speed of the particle? So the velocity is just the derivative, so component by component, -3 cosine squared t sine t in the I direction, 3 sine squared t cosine t in the j direction, and actually there's no z direction, and the speed is just the square root of each of the components squared. So that's it for the main points of this section. So next I have some review problems. These are 2 quick review problems for you to try. So you should stop the video, try the problems, and then on the next slide, there'll be answers. Here are the solutions. The problems are fairly straightforward. There's a little bit of trig here that I wrote out for you so you could see how I simplified it or completed this problem. And that's it for this video. Thank you for watching.